In this video, a parallel-sided glass slab has been taken. Now on this glass slab, a beam of light is incident. A part of this beam is getting reflected, as you can see, and another part is getting refracted and traveling inside the glass slab. And after the first refraction, it is falling on the second side and getting refracted again. So let us find out through a ray diagram what exactly is happening. Now here we have considered an incident ray PQ that is incident on surface AB of the glass slab. Now if we draw a normal at the point of incidence, that is Q, we will find that the ray PQ is making an angle I with the normal. So the angle of incidence is I. Now as you can see, the ray is incident from an optically rarer to an optically denser medium, that is from air to glass. So once refraction takes place, the refracted ray will bend towards the normal. So here we consider the ray after refraction. The green ray represents the refracted ray. Here, the angle that the refracted ray is making with the normal is R1. And as you can see, the refracted ray is traveling from surface AB to surface DC, as you can see by the arrowhead on the ray. Now at surface DC, we draw another normal at point R, because QR represents the refracted ray which is now incident on DC. So if we draw a normal IJ at point R, we can say that the angle of incidence for this ray at the second surface is R2. Now if you observe closely, the ray of light is incident from a denser medium to a rarer medium. So now the light ray will bend away from the normal. So after refraction, the light ray RS bends away from the normal and it forms an angle E with the normal. This angle is known as the angle of emergence. Now look closely at what is happening over here. The light ray that we had initially considered was light ray PQ. Now if the glass slab would not have been there, what would have happened to PQ? We extrapolate PQ and find that PQ would have traveled along this direction. But instead, when we place the glass slab, we find that ray PQ is not traveling along this direction. Instead, it is emerging from the glass slab along RS in this direction. So clearly we can say that the path of the light ray has been shifted. This shift in the path of the light ray is known as the lateral shift. Lateral means sideways. So as you can see from the diagram, ray PQ when extrapolated to S dash has shifted from the emergent ray, that is RS. So in other words, we can say that the emergent ray has been shifted from the original path of the incident ray. So this S dash is termed as the lateral shift. You will be interested to learn that the incident ray, that is the path the incident ray was supposed to be taking, and the emergent ray are parallel to one another. This is happening because AB and CD are parallel to one another. It is a parallel-sided glass slab, and thus the incident ray is parallel to the emergent ray. Now if we consider a ray of light PQ that is incident normally on the parallel-sided glass slab, what do you think will happen? The angle of incidence in this case is 90 degrees. So even though it is traveling from an optically rarer to an optically denser medium, we have seen that when the angle of incidence is 90 degrees, it does not undergo any refraction. So ray PQ travels straight inside the glass slab. Now since this is 90 degrees and since there is no refraction at this surface, and also since surfaces AB, that surface AB is parallel to surface DC, this ray is incident on surface DC also at 90 degrees. And since it is incident at 90 degrees at the glass air interface, it travels through without any refraction. So what can we say? We can say that when a ray of light is incident normally on one of the surfaces of a parallel sided glass slab, it undergoes no lateral shift and it emerges in the same path as that taken by the incident ray.